So, it's a pleasure to introduce Søren Fournais from the University of Copenhagen. He has given a beautiful talk on Bose gases last week in Merida, and now we changed the topic, as you can see, and go for tunneling formulae for magnetic operators. Søren, please, stage is yours.
Thank you, Vilker. It's a bit loud, isn't it? Or is it just me? Okay, well, I hear myself too loud. I'm not used to that. So it's a pleasure to be here. It's a pleasure to congratulate Vilker once again. And I decided that I wanted to give a different talk from the one from last week. And so this is really now for something completely different, tunneling formulae for magnetic operators. So first, okay, so the key word there is magnetic, right? And so this slide is about what people have done a fairly long time ago, namely the electric tunneling is fairly well understood from a mathematical perspective. Now, what I want you to think about is, here's the chalk. So we should have somehow a double well potential. I hope people can see just a little bit, but so imagine just having a potential that looks like kind of like this, with two identical wells separated by some barrier in between. Right. And so the quantum problem of tunneling in the, say, in the mathematical setting is that you have the kinetic energy of your particle, and then V you should think of as being a double well potential like that. And then the E, sort of you can formulate it in terms of different parameters, but the cleanest setting is often to think of it in a semi-classical setting, where you have a small parameter in front of your Laplacian, and then you want to understand somehow how independent are these wells. In other words, if you look at a particle that is isolated in one of the wells first, then how long will it take before it tunnels to the other side? And that can also be rephrased in terms of energies, that somehow how big is the gap between the first and the second eigenvalue in this system. Because if you imagine that the separation here between my wells is infinitely high, or in other parameters, you imagine that you have one well here and you have the other well, and that you allow to move away to infinity, so they're infinitely separated from each other, then you would have a spectrum which is exactly 2 copies of the one well spectrum, right? And so therefore, you would have eigenvalues, say, with multiplicity 2, because each eigenvalue that I see in this well, I would also see in the other well. Okay, and so the splitting between eigenvalues you can also think of as a natural measure of how much the different wells are allowed to talk to each other. Okay, this was a very important problem in the spectral theory community in the 80s, and in the electric case here, it was solved to a very high degree of precision by Barry Simon, and in particular Helfer and Sjöstrand well, roughly 40 years ago. Okay, and just to have sort of an idea on the slide of what I'm really talking about, in a setting like my drawing over here, that I'm in one dimension, I have a double well potential. What is this splitting? So I think of the difference between the second eigenvalue and the first eigenvalue of the double well problem. Then that is given as an exponentially small term. So it's e to the minus some coefficient divided by h. And then you can even calculate, there's some powers of h in front. You can even calculate the constant in front. You can calculate this to a very high precision. And the important part, which is this exponent here, this coefficient s, that is given by the Achmon distance between the bottoms of the two wells. So I didn't put parameters on my drawing over here, but I imagine that these wells here are minima situated at minus a and plus a, and that the minimum energy, I have put that to 0. and then my formula here for the exponent is true. Okay, and so what were the some of the mathematical techniques that were developed to handle this problem? Well, there was in particular the famous Argmon estimates in order to get exponential control of the decay of eigenfunctions, and then WKB approximations. Well, you could say those have been around in theoretical physics almost since the beginning of quantum mechanics, but you could get very, very accurate WKB constructions that are accurate up to exponential precision, and those are really needed and need to be constructed in the general setting that you are working on. Okay, so these are key words and key ingredients when you want to prove something like this. The problem is that as soon as you put in a magnetic field, then we actually don't know how to do. Okay, and part of this, the reason you have to think that this is difficult is that at some point you need to calculate kind of overlap integrals between eigenfunctions sitting in one well and eigenfunctions sitting in another well. Okay, and even getting so these are exponentially small, so getting them correct at this exponentially small scale, that is a challenge, and that is what was solved these 40 years ago. But if you have a magnetic field, then it turns out that these eigenfunctions, they're no longer just real positive functions in the region that is crucial. They are actually oscillating because of the magnetic field, and they're actually rapidly oscillating. It turns out, and I think that cannot really be guessed, but it turns out that in the situations that we're interested in, this oscillation is so important, is equally important to the exponential decay. Those two effects, they sum up and kind of on an equal footing. So what I'm trying to say is that this S here is really going to be different due to the magnetic effect. And so that's what was an open problem, almost generally open for these 40 years, and where in recent years we have started to see some progress. Okay. So, of course, putting in a magnetic field is that you take a magnetic vector potential and maybe a sort of a magnitude parameter B, and put that into your kinetic energy, as we all know in your Schrödinger operator. And from a mathematical point of view, I would say that this is such a natural extension of the theory that this is a problem that we have to be able to solve. Right? I mean, this we need to be able to solve, but at present it's actually still very open. Okay, and there was kind of a perturbative argument given in one of the papers by Elfer and Sjöstrand, but the magnetic fields have to be extremely weak in order to get a result, and also you have to sort of make sure that the geometry underlying is still completely determined by the electric field. So what the kind of questions that we would like to ask is really, well, what if the magnetic field is dominant? Say, what if actually these wells are not electric wells, but they are wells that are determined by the magnetic field? I mean, you could have a variable magnetic field, and then where the magnetic field is the weakest is where you would have the lowest possible energy. So you could actually have tunneling between just purely magnetic wells. Okay. Sorry? Yes, so in some of the results that I was about to mention here, the magnetic field is constant everywhere in space, and the wells are electric wells. Okay, and even that case of having a constant magnetic field and having two spherically symmetric, we're in 2 dimensions only so far, two radially symmetric electric wells, that was one of the kind of the simplest questions that people did not know how to solve up until 3 years ago. Okay. constant magnetic field uniform, we're in 2 dimensions, right? So the magnetic field is equal to 1 everywhere, okay? And there's no parameter B in front of it, there's just an H in a semi-classical parameter. So that kind of translates a little bit into having a large magnetic field in the limit that you're looking at, but nevertheless, it's not huge. Okay, and it was actually that situation, so the simplest possible, where you have a constant magnetic field, you have 2 electric wells there, it was open even whether this was an exponential decay with a 1 over h, maybe even whether the tunneling could be 0, whether it could have degenerate eigenvalues or not. But that has now been solved through a sequence of works, in particular starting by Pfefferman, Shapiro-Weinstein in 22. Okay. We have then tried to look a little bit at the purely magnetic case, and that's what I want to report about here. So I came into this from the magnetic theory of surface superconductivity, but that's a little bit more of sort of historical interest than really of interest to this talk. But that was also where the first positive result came from, because that's namely in the setting where you have where you kind of have a surface and everything then almost reduces to a one-dimensional problem. Then Virginie Bonaille-Noël, Nicolas Ramon, and Frédéric Héron succeeded both in making the first precise magnetic WKB constructions and also in getting the first magnetic tunneling result. But these were special situations where you had a reduction of dimension, so having really tunneling in a really 2-dimensional situation. Ideally, 3 dimensions would of course be great, but so far we are ambitious just to talk about 2. Was very much open. And I would like to maybe mention here that there was even a review paper where there was a suggestion that the magnetic tunneling should not be on the same scale. It should be on a square root h scale instead of a 1 over h scale. Okay, which is kind of a natural, if you think of, when you think of magnetic energies in a constant magnetic field, the eigenvalues would be h times b times some integer. And so therefore you see that the magnetic field kind of comes in with an extra h in front. And if you extrapolate from that guess, you would get this square root behavior instead, which turns out to be wrong. So the result will come in a second, but as I said before, we will be in 2 dimensions. So this will be a particle moving in 2 dimensions in a constant or slightly non-constant magnetic field. Okay, so that's this next slide. The setting is that we are in 2 dimensions. We take a purely magnetic Schrödinger operator, where the wells will now sort of come from having variations of the magnetic field. But think of the magnetic field as being essentially constant at infinity. The magnetic field in 2 dimensions, just to remind you, is just this sort of cross derivative of the vector potential which sits in here. And in our setting, the B will have to be smooth, actually very smooth. I will come back to that. It's strictly positive, and it will have minima. Okay, and again, I want you to think that minima of a magnetic field actually acts the same way as minima of an electric field. That is something you may or may not have encountered earlier in your mathematical life, but it's true. So therefore, in this setting here, the particle wants to sit near the minima of the magnetic field. And so if you have a magnetic field which looks a little bit like a double well, think of this drawing but in 2 dimensions, then the particle will want to concentrate at the bottom of one well or at the bottom of the other one. And there will be a potential barrier coming from the magnetic field that it has to climb to go from one to the other. Okay, good. And so what we want to do is we want to calculate the splitting between the second eigenvalue and the first eigenvalue of our operator, which looks like this. Okay, and so that is, I mean, of course you can discuss what the measure of the tunneling effect is, but for me, this eigenvalue gap here, that I expect to be very small, but even still, this is the tunneling effect for me. Good. And this is my example. What you should think of that you're looking at over here are the level curves of the magnetic field. So the coordinates in this example are called Q1 and Q2. So this axis here is Q1, and that axis there is Q2. And essentially in Q1, you have something that grows quadratically in Q1. That's this Q1 you have up here squared. Okay. In the Q2 variable, you should think of having this sort of double well potential over there. So in one variable, you take your favorite double well potential, except you need it to be bounded for technical reasons. And in the other variable, you just take a quadratic potential. Okay, and then again, I need boundedness for technical reasons. So in order to just have this whole thing, I have divided it by 1 plus Q1 squared, because then the whole thing becomes bounded. I mean, I can control of this. And I need it to be strictly positive, so I lift it up by putting in a 1 here, and then there's a B0 in front just to sort of say that I can deal with, say, arbitrary magnetic field strength, but really this is not an important coefficient. Okay, so that's my setting: a double well in one coordinate, a single well in the other, and I have 2 points here, which, I mean, at the drawing is -2 and 2, but those are called C up and C down. So C down would be down here, and C up would be this point up there. Okay, and now, once I have this, I need to go into the complex plane. Okay, so if I try to now say, okay, my particle wants to live at this energy sort of given by the scale B0, okay, I can try to solve when my magnetic field is equal to B0. Of course, if I only look at real solutions, then that's by definition this point C up and this point C down. But if I allow myself to go into the complex plane in the Q1, then for every Q2, I have two solutions, namely Q1 equal to plus and minus I times the square root of some epsilon, and then the value of my potential, my double well potential we're drawing over there. Okay, with this epsilon 3 just being the ratio of the previous epsilons. And that actually in some sense defines a complex curve from one minimum to the other. Right? It goes into the complex plane, but, well, that's what it does. Okay, so along this complex curve, it's purely imaginary. I have that the magnetic field on I times gamma, where gamma is now this curve of Q2 and Q2, that is the sort of the energy surface or the level curve giving the value B0. Okay, and gamma is given by what we saw up there that it had to be. Okay, this is kind of the input to my theorem, and my theorem tells me that this splitting that I want to calculate is given by, again, there's a coefficient, that's a power of h, but there's an exponentially small term which has kind of the same structure as before. It's a 1 over h, not a 1 over square root h in it. And what is this Agmund distance, this magnetic Agmund distance, if you want? Well, that's explained up here. There's a capital gamma, which is that I integrate in the Q1 variable out to this imaginary point, which was my curve, so from 0 to Q2, and then that I integrate between the two minima. Right? So really, I take, in some sense, a double integral. I mean, there's a real integral between the lower minimum and the upper minimum. And what is my integrand? Well, with my sign convention, this gamma here is actually strictly positive, so I can let go of the absolute values. And so my integrand is an integral itself, namely this this integration out to my complex point. I mean, so in some sense, this is a double integral of a magnetic field. So it's kind of a flux, but it's just sort of a flux of a magnetic field extended into the complex plane. Okay, and that's what gives me my exponential, my leading term down here. Okay, I wanted to state this as an example, right? I mean, I think this magnetic field is a little bit construed, but it's not completely arbitrary, right? And it's not completely strange. But of course, I have really put in the fact, even if it looks fairly natural, that as a function of Q1, it is a holomorphic function. So therefore, I can actually extend it into the complex plane. And so my theorem is valid for the example, but it's valid under some general assumptions that I will run through a little bit quickly because they're a little bit technical, but I somehow want to at least tell you that there is a theorem for a general class of potentials that works. Okay, and so the assumptions is that we have a smooth magnetic field, so smoothness in all variables is necessary, and it has exactly these two minima that my example has, an upper point and a lower point, and the magnetic field has the symmetries that my examples had, namely under reflection in the Q1 axis, okay, in the Q2 axis and in the Q1 axis. Okay, so I have these two symmetries, and these minima are non-degenerate. We could go further and try to discuss what happens if the minima are degenerate, but that would be a next work. Okay, and well, I made a choice of gauge on the introductory slide, and that choice of gauge is actually compatible with the symmetry. So if I change the sign of Q, then that commutes with my operator. Okay, those were sort of very innocent assumptions. The next is maybe where many of us will want to say that something better should be possible eventually. That is that we want to say that the magnetic field and the derivative of the vector potentials have to have some partial analyticity. So as a function of Q1, the magnetic field has to be analytic, and also the derivative of A2 has to be partially analytic in that variable. In some, you can go a little bit into the complex plane, okay? And you can even control derivatives when you do that. That is needed. And well, let me say that this here is essentially just saying that these epsilons that I put in, they were there for a reason. I need my variations to be small. I mean, there's a change of variable that I need to control by using the inverse function theorem, and therefore I need the variations to not be too large. Let me not talk too much about this. Yeah. Well, it has to be a symmetric double well potential that is smooth. Sorry? The wells are identical, yes. And because somehow the whole problem would be very different. If the wells were not identical, then kind of one well would be better than the other, and then there would, well, it would be a question of calculating the single well eigenvalues with sufficiently high precision to see the difference between one and the other. And that is, in some sense, a simpler problem, and we have other methods for doing this. So somehow the key thing here is to understand when they are different, right? Okay. Then you could make them exponentially different from each other, and we would have the same discussion. But somehow I feel that the key question for me here is when they are symmetric, and so that's an assumption. Good. And then the other assumption, which is key both for the proof and for formulating the result, is this fact that we have a complex path that connects the minima. Right? That was what we saw by simple calculations in the example, but we need that there is a smooth function, sort of a smooth path that lets you solve the the level curve, well, that gives you the level curve of size intensity B0. Okay, and well, that of course goes through the minima, and then you can choose it to satisfy derivative conditions. Okay, and this now gives you exactly the level curve or the level curves, right? I mean, you have one that goes into the positive imaginary part, but you also have its reflection that goes into the negative imaginary part, and these curves cross exactly at the real solutions to this equation, namely at these 2 points. Okay, and these are the complete level curves. I mean, there are no other solutions to this equation. Okay, that's the assumptions, and then the result is still what it was before, under these more general assumptions, but still, I mean, the drawing is for the example. Okay, so this was a lot of explanation of the result. I hope that I have time. I have also not looked at my watch, so I really don't know how much time I have left. 15 minutes. Okay, good. That's very good. So then, if there are any questions, I'm happy to answer them here, but if not, I will spend the next 15 minutes giving you some ideas of the proof. Yes. Not a simple reason. I mean, I think there the argument of, I mean, you might remember that in the electric case it was an H, power 1. Now I changed, but there what I said that was wrong, to guess the exponent, turns out to be right. Namely that this power H was somehow related to an integral that included an H, and then it included the electric field. Now, in this situation, the electric field comes from the magnetic field that comes with an extra H. Okay, and everything there had a square root. So it was a square root of V, and therefore there comes an extra square root of H. I mean, I can see that in the formulas when you calculate it, that's where it comes from. If you ask for a physical reason why should it be an H3 halves, okay, good. But so that's the reason why. But let me maybe stress. I mean, even though it's probably obvious to everybody in the audience, I mean, this is kind of an irrelevant lower order term, right? I mean, this is exponentially small. This is just a power in front. So the real, I mean, the key really is to be able to calculate that the power here is 1, and to be able to identify the coefficient there. To be able to identify the power of H that's out in front, that is like a next order question. We happen to be able to do that, but I would still be presenting this if I didn't know what that power was. No, because remember, this is the situation where we do not have an electric field, so there's purely magnetic. So it's not a question of turning on a magnetic field on an electric situation. It's a completely different system. If I am pushed hard enough, I have a formula for it, and I would be able to calculate it, yes. Well, I have a very, very ugly expression for it. I can calculate if I really, really have to. I don't want to, but I could, yes. Sorry? It's some number. Yes. Yes, and it's especially important that it's not 0 now that you're asking, right? Because again, if it was 0, then I wouldn't be as interested. I know that it's not 0. And I actually have a formula for it. But that was like, I mean, getting to that and making sure that C was not 0 was also crucial. Thank you. Okay, then I will go on with, well, maybe so not much the proof, but the ideas that go into it. Because, so what I'm saying is that it's really difficult to do magnetic fields because of these oscillations. And in some sense, we don't know how to handle really magnetic situations. And I should say that at the end of this work, we still don't know how to do magnetic WKB constructions. Or at least there are some works that I have not been involved in previous to this work that do produce magnetic WKB constructions, but we do not know that they are precise enough to do something like this. We tried that and it didn't work. Okay, so yeah. So precise enough is that really I need to understand the eigenfunction that sort of, if the proof will go by making one well a little bit higher than the other, so that I have a one well situation that is well defined, that the eigenfunctions need to be concentrated in that well, and then I need to understand the exponentially small part of such an eigenfunction that is localized close to the bottom of the other well. And I need to understand that to a precision that is better than this exponential term that I had. And that I need everywhere in that region. And I also need to understand the oscillations. So there are different Sobolev norms coming in, but think of having a pointwise uniform bound essentially in the bottom of the other well that is better than exponential. And that's what we can't do. Not just better than exponential, but better than exponential with the right power, right? With the right exponent. Okay, so that we don't know how to do, but what we do is sort of to reduce to something that we know very well, namely the constant magnetic field case in all of space. Okay, so how does that work? We make a change of variable. That's why the original variables were called Q, because we make new variables that are now defined by essentially the vector potential. Remember, the vector potential had only one component, so A2 is really everything there is, and Q2 is just mapped to X2. So think of what do you do in the right gauge with constant magnetic field. Well, there you really have that the vector potential is just one of your coordinates. So I want to place myself in that situation. And that I do by that change of variables. Of course, since this is really a change of variables, there are also some Jacobian terms that come in, so I cannot do it exactly, but am I still on? I'm still on. But it still sort of works. So once I implement that change of variables, I get a differential operator that has the magnetic field out front. That's kind of the way that it was set up. And then I have the derivative. So at this point, this psi here, I mean, there's a psi1 and a psi2. Those are just the component of the momentum with an h in front. Okay, so there's a second derivative in psi1, a derivative over here in x2. And then if I didn't have this alpha term, then it would be exactly the constant magnetic field case. Well, say if B was a constant. Good, and then how would I then diagonalize that? Well, I would make a partial Fourier transform in x2, in psi2, and then I would make a translation to kind of absorb that and really have just a harmonic oscillator in the x1 variables and nothing else. That's the way. That's one way of diagonalizing the harmonic oscillator, the constant magnetic field. If you do the same thing, right, under in this setting, then this sort of Fourier transform and translation, you can think of it as being a symplectic change of variables, so kind of a change of variable on phase space, not just on space. And you can implement it by a unitary sort of metaplectic transform, so you have an Egorov theorem, so you can calculate explicitly what it gives, right? And well, somehow you saw that there's like a difference between the x1 variable, which is the one that ends up being left, and the x2 variable, which is the one you translate away. And because of that, we make a scaling to make one of the variables semiclassic and the other one not. But that's just sort of technical. You don't really have to worry too much about it, but it's implemented on the slide. That's why I tell you. So once you've done that, so this is this scaling in the x1 variable, then you will get an operator that I call M, and I've smuggled out a power of h, which is sort of everywhere. So think of the h as being deleted, but I just wanted to put it there so you see that it gets taken out. And it looks like this. It's exactly like in the x1 variable, it's like a harmonic oscillator. There's the derivative here, and there's a square in the x1 variables, and it depends on the x2 variables, both space and momentum, but don't worry, parameters. So there's a coefficient here, which is the magnetic field. By the way, if you're worried about why the magnetic field is now a curly B instead of just a standard B, that's because it's really curly B in the magnetic field in the new coordinates, and that's why I have changed notation. So it's the magnetic field, and then there's this alpha term, which comes from a derivative of the vector potential. But I mean, that's a technical thing. So essentially, if I think of freezing x2 and xi2, then I just have a harmonic oscillator here in the x1 variables. And that's something I know very well. Okay? Now, of course, this is still, I mean, this is really operators, right? We still have that it depends on these variables, but I can think of now having understood that this is a harmonic oscillator depending on some parameters. And now in some sense you can say that I have one, right? Because the harmonic oscillator, that has an electric potential. It's an electric problem, not a magnetic problem anymore. So you can hope that in these coordinates, you have not as many oscillations, not as many bad oscillations as you had in the original coordinates. And notice that what I have done here really is that I have changed variables, but I have also made this sort of symplectic change of variables. So getting an approximation in these coordinates really doesn't amount to a WKB construction in the original variables. It's something completely different. It's a very different ansatz for what your wave function should look like. Okay, good. But so that is the setup. And in here we can now start doing the calculation that we talked about 5 minutes ago. Namely, that now I need to understand to very high precision, to exponential precision, what the eigenfunctions look like. Okay, in order to do that, I seal one of the wells, meaning that I sort of add a little bit potential to one of them so that I get a one well problem effectively. Okay, and now I want to get exponentially good bounds, and the best way to do that is to conjugate by an exponential weight. So I conjugate by an exponential weight, and then my m becomes decorated by my exponential weight up here, which is now something where by necessity I will have changed my xi by the derivative of my weight, and that comes with an I in front, so I need to be able to go into the complex plane in that variable. And that's why I need holomorphicity or analyticity at this point. Okay, and that goes on both sides. Okay, and so this is again, it's kind of a harmonic oscillator. There's this extra potential from the other well that doesn't really matter so much at this point. And you see that now I have a complex magnetic field here because I've gone into the complex plane. But still, I mean, even if it is complex, this is a non-self-adjoint operator, but still as a function, I mean, as an operator just in the x1, x2 variables, it's still an operator where I know the spectrum. It's still given by the Landau levels. It's just, I mean, Landau levels are now complex instead. Okay, this is one of the good non-self-adjoint operators where we can actually still calculate the spectrum. Okay, and now you need to analyze these operators in very high detail, and I have not put all of that on the slides, but once you know that you can make these complex sort of conjugations, these exponential conjugations, then you need to know that you still have sufficient control of sufficient coercivity, and then you can still get away with proving exponential bounds on and good eigenfunction estimates on these functions. I will not go through that here, but that is, there's a long analysis of essentially this operator here, long and detailed analysis that will be left for some other day. Okay. The rest of this is essentially the standard setup that just to tell you how you actually calculate this gap, and that essentially goes back to the works of Helfer and Sjöstrand and maybe even before. So once you have a good approximation from one well and a good approximation from the other well, then you take the, so you have the upper ground state, that's the one well eigenfunction corresponding to one of the wells, and then you can make a down eigenfunction just by using the symmetry. You cut off the upper function so that it doesn't see the real bottom, but it goes almost all the way to the bottom of the other well. That gives you the f that is not bold, and the same with the down. Okay, where these cutoffs are exactly what I told you. They sort of cut off just a little neighborhood near the bottom of the other well. Okay, if you just plug these in, then they're exponentially good trial states, and that gives you bounds like this, that the full operator on one of them, and you take the one well eigenvalue, that then this part here is exponentially small, telling you that the f star is a very good approximation to the eigenfunction. Mu1 is an exponentially good approximation to the eigenvalue, with this error here, which is a little bit worse than what we need. So these are rough bounds. They're exponentially bound, but they're not good enough. And it also gives a bound on the gap, but again, it's not good enough. It's slightly worse than what we need. And the way to improve the precision is to actually, in some sense, do a calculation with a 2x2 matrix, which is amazing. You look at the two-dimensional space, which is the space of the true two first eigenfunctions, and you project on that. And now you take your approximate eigenfunctions, you project on that space, you will get a two-dimensional space in a two-dimensional space, so you will get a basis for your space, because these were fairly good, so they are not projected out of the true eigenspace. Okay, once you have projected there, then you do the usual Gram-Schmidt orthogonalization, and a small calculation will tell you that once you have gone to that basis, the true splitting is given by the eigenvalues of this 2x2 matrix, but this 2x2 matrix that you have constructed has an off-diagonal term, and so therefore, once you diagonalize it, you will get that the off-diagonal terms change the eigenvalues a little bit. Okay, and so in order to understand the splitting, you need to understand this off-diagonal term. Okay, let me stress here that this is up to, again, an exponentially small bound, but where now we have 2 in front from the geometry coming in. Okay, and so if the exponentially bad bound we had before was so good that 2 times it was good enough, then we have 1 at this point. But of course, we don't know that until we have calculated W. Okay, and well, W you can write out what it is. It's essentially your operator acting on say the one well eigenfunction and then sandwiched with the other one-well eigenfunction, and that's what when I talked from the very beginning about overlap integrals, it's this overlap integral, right? I mean, this is really taking the eigenfunction from one well and then acting with a differential operator on it, and then seeing what is left of that when you get to the bottom of the other well. And that's the overlap integral you need to understand. You can write it out in terms of the weights that we have. And then this is really the integral that contains all the information, all the constants you need to extract, all the powers you need to extract. The fact that you get the right exponent in the end comes from the fact that the sum of these weights is constant equal to this power s that we had. That's where the exponential bound comes from. And then, well, if you want all the other information, in particular, you want to know that this is non-zero, then you have to calculate the integral, and that comes from the stationary phase theorem and quite a bit of work. And I think the chairman is moving, so I think I should finish. We have established what I think really is the first formula for a purely magnetic tunneling effect in a somewhat generic situation. I mean, I had lots of assumptions, but I mean, you could make small perturbations at least and still be in the same situation. These adapted coordinates came essentially from the thesis of Léo Morin, that was joint work with Nicolas and Saint-Vougnoc. And as I have stressed once before, we really did not construct magnetic WKB solutions, so that we still don't know how to do. And of course, we would like to have the same kind of theorem with much looser assumptions, but that's hopefully, well, it's work in progress, but I think it's work also, a lot of future work. This was the theorem. Congratulations, Vilker.
Thank you very much, Søren, for this beautiful talk, for the congratulations. Let's open the discussion. Other questions? I would like to ask one question. Hold on. You have already asked a lot of questions, I believe. The function phi you introduced, is this a real function or is it
the weight function phi is real. Yeah.
Okay, thank you. So, other questions? Yes, please.
Well, thanks for I think it's a great question. I mean, it came from us standing in front of a blackboard not knowing what to do. But let me expand a little bit more on that in the sense that, so these, I mean, what I presented was joint work with Léo Morin, Nicolas Raymond, and Yannick Guédès-Pontonneau. I think I forgot to say that, but it was written on the first slide. And then, of course, sort of this change of variable, well, these guys knew about that. I think at the time originally when that work was done, the idea was very much to go into these magnetic WKB constructions, which was actually, I mean, one of Nicolas and San's sort of next works after Leo finished his thesis. But somehow that program didn't come through, right? I mean, these WKB constructions, well, they may or may not be good enough, but so far we really cannot get them to work. I mean, so what we thought was, well, okay, if that doesn't work, then what do we do? Okay, and this is what we came up with. That is not a very scientific answer, but it's an honest answer.
Okay, please.
First of all, let me ask you. Once you consider matrix 2 by 2, you get additional term exponential of minus 2s over h bar. That's correct?
So you say that I get this power raised from 1 times s to 2 times s. Is that's what you're saying?
That's
yes.
Correct. But if you consider matrix 3 by 3, I suppose you will get the same exponential, but with factor
but see it. So the structure is different, right? Because why is this a 2 by 2 matrix? It's because I have that. I know beforehand by a rough analysis that the first 2 eigenvalues, these 2 here, they are very, very close together compared to the next one. And if I were to take the next one or the next two, if you want, because they're also like a package of two up there, I could make a 4x4 matrix, but these contain next to no information about the eigenfunctions corresponding here. So adding those would not help me raise that exponent. No, unfortunately.
Let me make prediction. If you do things right, you will get exponential of 3s, 4s, etc.
By taking larger and larger matrices?
Larger matrices. And this construction is known, not in mathematics, it's known in physics. And this construction is called instanton calculus.
Instanton calculus.
Instanton calculus. I will in a minute say what is this. But furthermore, this series of exponentially small terms, it's also known, and it has now a name, it's called trans series. So in addition, in standard perturbation theory, when in addition to Taylor expansion, you have also infinite expansion in exponentially small terms.
That's very interesting. Yeah.
And now just a couple of comments. Long before Barry Simon, when he was a little boy, this calculation of exponentially small term was made by George Gamow when he studied alpha decay. It was 1930s. Furthermore, this is first comment. The second comment, you consider in fact a double well potential. But a double well potential, if you go to Euclidean space, so double well potential is inverted. So you have potential of this type. And you can study in path integral approach, really tunneling from one maximum to another. Once you go from one maximum to another, this trajectory exists, and this trajectory is called instanton trajectory. And if you calculate action on this trajectory, in physics, S, what you call it's called action, you will find you will find the action. If you consider so-called two instanton trajectory, once body goes from one maximum to another and then goes back, this is so-called two instanton solution or two soliton solution, whatever. You will get a doubling of exponential, and etc., etc. If you take several, etc. So this is, in a way, what you are saying. To my great amusement, you definitely, without knowing instanton calculus, reproduced a certain basic results there.
Okay, so I think we should. That's good. Thank you very much for that. No, let's just. We are running into the end of the coffee break. I propose we leave this to a private discussion. Thank you very much.
Thank you.
And I think we resume here in somewhat more than 20 minutes, 10:06 for the last talk. Yeah, and now we have a coffee break, and then. I'm sure that Søren would like to get to know about this instanton calculations. Thank you very much again, Søren.
Thank you.